Hi, welcome to my channel. Today we have a quick and simple proof to work on, which is based on some rudimentary number theory. So let's see what we have. We want to prove that if m is a positive rational number, then this number m plus its reciprocal is an integer if m is 1. Well, let's see how to tackle this problem. M is a rational number, so let's express m as a fraction with a numerator p and a denominator q. Now, because we're assuming m is a positive rational number, let's make p and q positive integers. This ensures that our fraction is indeed a positive rational number. And at the same time, let's assume that this fraction is in lowest terms, which tells us that the greatest common divisor of p and q is 1. Okay, well, under this setup, what is m plus 1 over m? Well, it's simply this fraction, m, plus 1 over m, the reciprocal of this. The reciprocal of p over q is just q over p. And if we simplify this into one fraction, we obtain the following. Now, for m plus 1 over m to be an integer, in other words, for this to be an integer, that means p divides the numerator as well as q. However, if p divides this sum, p squared plus q squared, that means p divides each of these individually. And likewise, we have the same situation here. If q divides this sum, p squared plus q squared, then q divides both p squared and q squared. Now, we see something interesting here. In this case, we have p divides q squared, but that can't be, because then p and q would share a common divisor. We assumed that p and q didn't have a common divisor except 1. And the same argument holds over here. If q divides p squared, that means they have a common divisor. But we assumed p and q only have a common divisor of 1. So for p to divide q squared, or for q to divide p squared, that means both p and q must each be 1. But if p and q are each 1, remember, m is the fraction p over q. And that's 1 over 1, or just 1. So indeed, if m is a positive rational number, then adding it to its reciprocal turns out to be an integer only if m is 1. And that completes our proof.